Scientists at NASA have made an extraordinary announcement. The Hubble Space Telescope has detected a galaxy located an astonishing 13.4 billion light-years away. In the image they released, a small red object marks the farthest galaxy ever discovered. However, this discovery is only a part of the story. The James Webb Space Telescope known as JWST has once again exceeded expectations and redefined the boundaries of cosmic discovery. In a development that many believe to be impossible, it has surpassed what's known as the Edington Limit during its observations, offering an unprecedented glimpse into the heart of the early universe. This achievement culminated in a detailed zoom-in on GN-z11, the most ancient galaxy yet observed. GN-z11, already famous for existing at a staggering redshift of 11.09, has now been brought into even sharper focus by the JWST's remarkable power and sensitivity. The implications of this event stretch far beyond astronomy. They challenge some of our most fundamental assumptions about the behavior of light, matter, and the very structure of the universe in its earliest stages. The Edington Limit is a crucial concept in astrophysics. It marks the point at which the outward pressure from radiation equals the inward pull of gravity in a luminous object. Normally, this acts as a natural cap. If an object emits more radiation than the Edington limit allows, it should, in theory, tear itself apart. So, when an observation appears to exceed this threshold, it either means the instrument is exceptionally powerful or there are unknown forces or mechanisms at play. For JWST to appear to break this limit while observing GN-z11 points to both its technological excellence and the possibility that our understanding of high-energy cosmic physics may need to be revised. GN-z11 lies more than 13.4 billion light-years away in form just 400 million years after the Big Bang. That places it in a time when the universe was still in its infancy. In studying this galaxy, scientists are effectively looking back in time, observing a chapter from the very beginning of cosmic history. Previous tools like the Hubble Space Telescope gave us hints of GN-z11's complexity. But it wasn't until JWST used its state-of-the-art infrared instruments that the true nature of this ancient galaxy could be revealed. JWST cut through the haze of the early universe with astonishing clarity, transforming what had been a fuzzy point of light into a rich and detailed portrait of structure and motion. These zoomed-in observations of GN-z11 revealed a galaxy far more organized and chemically advanced than anticipated. It was expected to be a chaotic mass of star-forming gas, but instead, it showed spiral-like formations, distinct star clusters, and even cloud-like nebulae. These details are astonishing because they go against the prevailing theories of early galaxy formation. According to current models, galaxies this young should still be turbulent and unstructured, having formed in the chaotic wake of the Big Bang, yet GN-z11 already shows signs of maturity. One particularly surprising feature is the presence of heavier elements like carbon and oxygen inside GN-z11. This indicates that several generations of stars must have already formed and died to enrich the galaxy's interstellar medium. The problem is, according to traditional timelines, there simply hasn't been enough time for that to happen. This suggests that star formation and evolution may have occurred on a much more accelerated scale in the early universe than we previously thought. JWST's success in resolving such fine details stems in part from its unparalleled sensitivity to infrared light. As light from GN-z11 traveled across the expanding universe, stretched from visible wavelengths into the infrared range, JWST was specifically engineered to detect this type of ancient redshifted light. Its segmented, gold-plated mirrors, designed with extreme precision, captured the faint signal from GN-z11 and fed it into its powerful spectrometers and cameras. This allowed astronomers to unravel the layers of the galaxy's structure with unmatched clarity. But perhaps the most astonishing aspect of this discovery is what JWST found at the core of GN-z11. There, scientists observed a compact object, possibly an early black hole or a densely packed cluster of stars, emitting energy that theoretically should have torn it apart? The fact that it continues to exist challenges the integrity of existing models of galactic and stellar physics. Could it be that different rules applied in the early universe? Or are there still undiscovered processes that help regulate such immense energy output? Using JWST's near-infrared spectrograph on IRSBC, scientists analyzed the light coming from GN-z11's core. The data showed clear emission line signatures of highly ionized gas traveling at speeds approaching that of light. This kind of activity is typically associated with either rapid star formation or the presence of an active black hole. Either way, it represents a level of energetic intensity that violates current expectations and aligns with the idea of surpassing the Edington limit. If a black hole is indeed present and consuming matter at such a pace, it implies an entirely new and much faster pathway for black hole formation in the early cosmos. This has enormous implications. First, it suggests that supermassive black holes could have formed in a matter of hundreds of millions of years instead of billions. That directly contradicts the traditional model, which posits that these behemoths grow slowly through gradual accretion and mergers. A faster route may involve the direct collapse of massive gas clouds, or the birth of black holes that skip several evolutionary stages entirely. Second, GN-z11's structural coherence poses a major mystery. How could a galaxy so young already look so organized? Observations show defined populations of stars, signs of rotation, stable, shape including features resembling spiral arms. These are qualities usually reserved for galaxies that have had billions of years to settle into shape. Their presence in such a young system flies in the face of hierarchical galaxy formation models, which propose that small, irregular protogalaxies merge over time into more structured systems. It's possible that GN-z11 is simply an anomaly in early cosmic overachiever. But if JWST uncovers more galaxies like it, then cosmology may need a serious overhaul. Another possibility is that GN-z11 formed in an unusually dense region of the early universe, where matter clustered quickly and gravitational interactions helped accelerate its evolution. This would mean that the large-scale structure of the universe began forming much earlier than our simulations currently predict. Technologically, the JWST's ability to capture GN-z11 in such detail is a triumph of human engineering and international collaboration. Its primary mirror, spanning more than 6.5 meters, has over 6 times the light-gathering power of Hubble. Located at the cold, dark Lagrange point 2, JWST can observe faint cosmic signals with almost no background noise. Combined with the powerful emissions from GN-z11, this produced an unparalleled dataset. Scientists were able to map the galaxies, stars trace its gas and dust, and even begin to chart its star formation history. One especially intriguing discovery was GN-z11's surprisingly low dust content. Despite its high levels of heavier elements, dust, often formed by dying stars like asymptotic giant branch, AGB stars, and supernova, is key to cooling gas and triggering new star formation. The lack of it here suggests early star formation may have followed different rules, perhaps shaped more by ionization feedback than by dust-driven cooling. This insight could significantly change our understanding of how early stars and galaxies came to be. Despite its small size, GN-z11 is forming stars at an incredible rate. Its star formation rate rivals, or even exceeds, those seen in galaxies. Many times its size. This kind of efficiency might be driven by internal processes compressing gas quickly, or by the surrounding environment. But this intense pace likely can't last. GN-z11 may already be entering a quieter phase, or may soon run out of fuel for such rapid growth. Another fascinating aspect of the observation was evidence of gravitational lensing nearby. While GN-z11 itself wasn't lensed, subtle distortions in the surrounding region suggest the presence of massive foreground structures, possibly dark matter, halos that could magnify or stretch background light. This points to GN-z11 existing near or within an early protocluster of galaxies. If confirmed, it would mark the earliest known formation of such a large-scale structure in the universe. This proximity to other massive objects could help explain GN-z11's rapid development. Gravitational interactions and dense environments often boost star formation and structural growth. If GN-z11 is part of a nascent galactic community, it might not be a lone wonder but the brightest member of a thriving early ecosystem. JWST will continue to study this region, searching for companion galaxies, intergalactic filaments, and other signs of a developing cosmic web. We're only just beginning to understand the true nature of GN-z11 and what it reveals about the early universe. Future observations may rewrite entire chapters of astrophysics. As the JWST continues to scan the sky, it's clear we're on the edge of a new era in cosmic discovery that may forever change our view of the universe's first moments.